Action potential. Action potential refers to the fundamental means of communication in the nervous system. Action potential represents rapid reversals in voltage across the plasma membrane of axons. The plasma membrane is selectively permeable. These positive feedbacks are mediated by voltage-gated potassium and sodium ion channels found in the plasma membrane. The distribution of voltage-gated channels along the axon enables the conduction of the action potential from the nerve cell body to the axon terminal. At this synapse, the electrical signal is converted to a chemical signal that is then propagated to the postsynaptic neuron. The sodium-potassium pump on the action potential contains 4 main phases. Those 4 main phases are the resting state, depolarization, repolarization, and hyperpolarization. When the neuron is at rest, only a small subset of potassium channels are open, permitting potassium ions to enter or exit the cell based on electrochemical forces. It is important to remember that there is no net movement of potassium ions. For each potassium ion that leaves the cell, another returns. Maintain the membrane potential at a constant value. Before I explain the sodium potential pump in greater detail, it is important to remember a few basic things about ions. Positively charged ions have less electrons but higher electrical potential, while negatively charged ions have a surplus of electrons and a lower electrical potential. In addition, it is important to remember that in an excitable cell's resting potential is -70. Extracellular refers to solutes that are outside of the cell, and intracellular refers to solutes that go inside of the cell. This brings us to resting potential. The resting state refers to when the activation gates on both the sodium and potassium channels are closed and the membrane's resting potential is maintained. Next, we have the threshold. The threshold, which is right here, it's the stimulus opens activation gates on some sodium channels. Sodium ions influx through those channels, depolarizing the membrane. If the depolarization reaches the threshold, it triggers an action potential, which you get right here when it goes up, depolarization. Next, depolarization. Depolarization opens activation gates of most sodium channels, while the potassium channel's activation gates remain closed. Sodium ions influx makes the inside of the membrane positive with respect to the outside. Repolarization. Repolarization, the inactivation gates on most sodium channels close, preventing sodium influx. The activation gates on most potassium channels open, permitting potassium influx, making the inside of the cell negative. Lastly, we have hyperpolarization. Hyperpolarization occurs when the membrane actually depolarizes beyond the resting membrane voltage, which you have right here, also known as the refractory period. This occurs because more potassium channels are open at this point than during the membrane resting point, allowing more positively charged potassium ions to leave the cell. The recovery phase refers to the membrane's return to a steady state as the additional potassium channels that opened during the action potential now closed, bringing us back to state 1, resting state. The membrane potential is now determined by the subset of potassium channels that are normally open during the membrane's resting state. The membrane is now back at a -70.